Get what I mean? So if I have the mass here, this would be my equilibrium line, and this would be where the mass stretched it, where this distance is my x, right? X is just the distance away from its initial. And so we would get mg is equal to negative kx. Or the actual position, x is equal to mg, or negative mg over k. Well, what do I mean by that? Normally, I would just say that this is the negative direction, or this is the positive direction. So, if equilibrium position is 0, then x would be a negative number, which makes sense here. M is some positive mass, k will always be a positive number, and g is 9.8. So making it all negative works out in the end for us. Now, that's all I can say on the spring force for now. There's nothing really else that I can do until we reach oscillations. Springs and pendulums, oh boy, that's going to be fun. So, with that under wraps, we can talk about centripetal force. All right? Which is pretty much circular motion. All right? I'm standing in the middle here, and I'm swinging a bucket full of water all around me. I'm assuming that gravity is pointing into the board, which means I'm looking at this from a bird's eye view. All right? Now, I'm going to define a lot of variables because we're not going to really delve into circular motion all that much today. I'm going to assume I swing it in a circle, and that circle has a radius of r. I'm also going to assume that it moves at some velocity. So r will be my position vector here, and then at here it has some other position vector, and another position vector here, and another position vector here. At this point, my velocity is going to look like this. At this point, like this, and like this, and so on and so forth. All right? If I have two, the velocity is changing, right? We'll assume that my velocity has a constant value. So it will always remain at the same tangential speed, where its velocity is tangent to the circle, and it will always have the same length, right? But what we don't assume, or what we can see then, is since the velocity direction is changing, velocity is changing. So there must be some acceleration at play here. Let's say a tiny distance over here, I have another velocity that's like pointing this way. If I take these two vectors and compare them, I'm going to have an acceleration pointing this way. If I bring these two vectors closer and closer, the acceleration vector ends up pointing more and more toward the center of my circle. All right, and so what I end up getting is an acceleration that's pointing inward at every single point. All right, this acceleration is called centripetal acceleration. And centripetal acceleration is just going to be equal to v squared over r. All right? Now, what do I mean by this? This is some definition that we can talk about, but we're not going to really delve into rotational variables until later on. So I want you to take this on faith for now. There will be more about this as time progresses. But for now, just kind of trust me. This is just how we define centripetal acceleration. Or we can do a little dimensional analysis here and say, all right, well, the dimensions of acceleration are dimensions of meters over a second squared. So this dimension should also be the same. So the dimensions of velocity squared over position would be something like meters per second squared per meter. Well, that makes sense. We'll end up just getting meters per second squared. which work out just as we intended. I'm going to define a few more variables. Assuming this bucket has a mass m, I'm going to define my centripetal force to be m times ac. According to Newton's second law, it's always ma. And where ac is v squared over r. So we get mv squared over r. All right? And this is true. Now, what we can do here, I'm going to define a couple other things. Assuming this has a radius of r, what would the entire length or circumference of the circle be? 2 pi r. So the entire circumference would be 2 pi r. Now, what about the velocity then would be the distance over the time it takes to travel around one revolution then. Okay? Then I'm going to rewrite my time to be c over v, which is going to be 2 pi r over v. Time here is like for one rotation. We call this variable a period, right? So one period is the amount of time it takes for one rotation to happen. All right? I'm going to do another thing then, where I say 1 over t is another variable called f. T is not tension and f is not friction. This is what's known as frequency, where f is just going to be v over 2 pi r. And one more variable here, omega, which is 2 pi f, is going to be v over r. This quantity here is what's known as angular velocity, or angular frequency. This is the first of many, and we'll see a couple lectures from now, angular variables. Rotational kinematics is one of the most pretty things in physics, in my opinion. But I can use this instead of v and say this is m omega squared r, where omega is just the v over r. And you can see now this will be v squared over r squared times r, which is v squared over r. It matches up perfectly with the centripetal force. That being said, I think that's pretty much it. What time is it? It's exactly 5. So this took under an hour and a half to cover everything. I can go over a couple more force examples with you if you'd like to stay a little bit longer. Your choice.
I'm okay.
You're good?
I'm good.
All right.